Hello, so we're at question 9 on page 36. Right, so they say there we have a reaction of copper carbonate that reacts with hydrochloric acid to give you copper chloride and water and carbon dioxide. Now, the phases here are quite important. They say this is a solid, this is aqueous, that is also aqueous, this is a liquid, and then they say that is a gas. Right, so there they give you the apparatus and they tell you when we have these things together, the mass of the container with everything in it is 170 grams. Now they ask you at question 9.1. Say two ways in which the rate of the reaction can increase. So here's, we said there's always 4 things that we can change. 1, 2, 3, 4. The first one we said is the state of division. Okay, so powder or solid or whatever. Then the next one is the concentration, and that is a concentration of hydrochloric acid. We can't change the concentration of that. The state of division is for the copper carbonate. Then the next thing is the temperature that we can change. We can't change the temperature of a solid, but we can change the temperature of the solution. And the last one is we can add a catalyst. Okay, so you'll get a mark for any one of those two. Right, then question 9.2. They first give you a graph there. Now, the graph there is quite important, and I'm going to paste it in here. I just want to crop it a bit. Okay, so you must be able to read this graph quite well. Okay, so here you can see we have pure and impure. You can see that they both start at 170, and then they end at different levels. Why do they end at different levels? The impure one ends at a much higher level of the contents. Why? Because with impure there's less products that's produced. Why is there less products produced? Because the acid must first eat through the impurities, so it will have less left over to produce the stuff that we want to do. Then the next thing here is, because this is quite weird divisions or different or whatever, what we want to do is we want to make sure that we have the correct readings. Okay, now I'm going to zoom in I'm going to zoom in here. You can see there's 10 lines in between. Okay, so there's 10 lines, and then you can see from here until here how much has changed. There's changed 0.05, because if you add 0.05 to that, then you get that. Okay, so that means one line, if we divide those two together, one line, so one strippikie daar is 0.005. Okay, so that is important that you have that, because we want to get the readings of there and there in a while. Okay, so yes, that is what I want to show you there. The first question at question 9.2 is write down the reaction time for the reaction of pure copper carbonate. Okay, so when did it finish, the pure one here? So you can see, you can take it from where the line starts to become a horizontal line. Okay, so you can see, I'll say somewhere there. Sorry, but I saw that in the memo they do take from 42, which is there, until 50, but I'll say it's somewhere there, 44, 45. So I'm going to say for myself 45 seconds. If you say 44, doesn't matter. Then they say, assume that all the gas formed during the two reactions escape from the flask and that the impurities do not react. Okay, so why is that important? You can see that they end at different masses. So you can see they both start, then they end at different masses. So when it reacts, the mass becomes less. Why do the mass become less? Because there is a gas that is formed. The carbon dioxide gas is formed, and that is released into the atmosphere. So I'm going to write here Again, the reaction copper carbonate plus 2 hydrochloric acid, I think, gives you copper chloride plus water plus carbon dioxide. Now, because carbon dioxide is the only gas, you can see in the picture the gas can escape. Then at the beginning, they said all of that at the beginning is 170 grams. And then they say at the end, the carbon dioxide gas has escaped. And so the rest, all of that is the mass that is left over. Okay. Alright, so that is quite important that you can see and read that. So I'm going to just explain why again. You can see in the container that the carbon dioxide is a gas and it is released up in the atmosphere. So beginning, the mass of 170 grams was everything, and then the mass of the end is, and we'll read it from the graph in a moment, is everything except for the carbon dioxide, because that is released into the atmosphere. Okay, so if you see there, where am I with my question? If you see there, if we must take our readings from here, so I want to get, what is the reading, in that line there, so up until there, just want to check that I'm on the right line, yes, and this one is up until there. Okay, so I can go calculate what is the readings there. In a moment. The first question at question 9.3.1 is they say calculate the average rate of the reaction for pure sample over the first 20 seconds. So the rate, you look at the y-axis, it's the mass, the change in mass over the change in time, and they say for the first 20 seconds. So we have 20 seconds at 10 minus 0. Now we know the mass at the beginning is 170 grams. We must just now find on the graph the mass after 20 seconds. So there's 20 seconds. The mass after 20 seconds is there. Right, so we want to get there. We know now that each line is 0.005. And there's 2 lines there. So you can say, right, I'm going to take that value there. I'm going to say 196.75 plus 2 times, and every line is so much. So that gives you 169.76. Okay, so that is the value there, 169.76. Okay, so that is the mass that we have left over after 20 seconds. So that is 169.76. And if you do your calculation there, you get an answer of minus 0.012 grams per second. You say, right, I don't want a minus, so I must make it a positive. I must make that a negative and that a negative. Then the next question, they ask 3.2. Calculate percentage purity of the impure sample. Now, the percentage purity formula is not on your data sheet. Okay, you also don't have to write a formula. You just need to know percentage purity is always the smallest value over the bigger value times 100. Okay, because you can never get a bigger percentage than 100. So if you look here, if you look at the graph, what we want to get is for the pure one, how much was left over, and for the impure one, how much is left over. Because then we know the difference between them there, obviously, is the impurities. Okay, so we want to get that value there and that value there. So we're going to count. We're going to say, okay, from 196.7, how many lines did we go up from there? We go up 1, 2, 3, 4, 5, 6. So that is plus 6 times 0.005. And from here we went up 1, 2, 3, 4, 5, 6, also 6. So that is also plus 6 times, 0.005. Oh, that looks like a 6, 5. Okay, so then you get here 196.73, and here you get 169.78, if I'm not mistaken. Yes. Okay, so that is the value that you have left over. So if I go back to my next page, then we can say, all right, at the beginning we have pure and we have impure substances. Okay, the pure altogether at the beginning was 170 grams. That is everything. Okay, then at the end we have 169.73. Was I correct? 196.73. That is everything minus, let's make these just arrows, that is everything minus carbon dioxide, because at the end we said that was at the beginning the mass, and then the carbon dioxide was released into the atmosphere. So what we have left over is everything that minus the carbon dioxide. So if we subtract these two from one another, if I subtract 170 minus 169.73, then I get the mass of the carbon dioxide, and that is 0.27 grams. I can do the same for the impure. At the beginning it was 170 grams, that was everything. Then at the end I had 169.78, am I right? 169.78, yes. So that again is everything minus carbon dioxide. So if we want to get the mass of carbon dioxide, we're going to say 170 minus 169.78. And that gives us 0.22 grams. Okay, so when we had a pure substance, that is the amount of carbon dioxide we gained, and when we had impure, that is the mass of carbon dioxide that we gained. Now, why are we looking at that? Because the ratio of carbon dioxide to copper carbonate is 1:1. This is 1:1, and because they told us this is in excess, and they said there's an excess, so it means we have limited of that, so everything is used. So if everything is used and the ratio is 1:1, then we can say, okay, the carbon dioxide will give us how much we have used there, what is the impurities there. Okay, so that is why we look at carbon dioxide, even though they ask for the impure copper carbonate. Sorry. Okay, so to calculate percentage purity, you must always say the smallest one over the biggest one. So you're going to say 0.22 over 0.27 times 100, and you get 81.48%. Okay, so that was quite a difficult one. Then question 9.3.3. Now say calculate the maximum volume of carbon. So they asked for the volume of carbon dioxide, that is a question, that's produced during the reaction of pure copper carbonate. So we are here with the pure, so the mass of the carbon dioxide that is produced is 0.27 grams. And they say under standard conditions. So standard conditions means STP, so it means we can use the volume at standard conditions is 22.4. Alright, so they want the volume. If we want to calculate the volume, we must use the formula mole is volume over volume at STP. So we must first calculate the mole. So that is what we'll use the mass for. So right, mole is mass over molecular mass, 0.27 divided by 44. And that gives you 44 is the molar mass of carbon dioxide. That is 6.13 times 10 to the power minus 3. Now we want to calculate the volume. So that is 6.13 times 10 to the power minus 3. We want to get the volume over volume at STP. So the volume is 0.137 decimeters cubed. Okay, so that was quite a difficult question. Then at question 9.4, they ask you sketch a graph, okay, of volume versus time. So we have time in seconds and we have volume, and they want the volume of oxygen. that was measured in decimeters cubed. Okay, now the same thing as with projectile motion. You're going to make a line, you're going to say time versus volume. We know at the beginning the time was when the time was 0, we haven't produced any oxygen yet. Remember, not oxygen, sorry, carbon dioxide. So we know at the beginning that is one of the products. We haven't produced it yet. So at the beginning, sorry, this must be carbon dioxide. The volume is 0. Then we said your first question that you've answered there is how long did it take? If you said 45 seconds or 42 or 50, whatever. So we know after so many seconds, what is the volume that is produced? You have just calculated there. We have calculated to be 0.137. Okay, now with this, the gradient gives us the rate of the reaction. Okay, and from this graph, you can see that the rate is not constant. You can see it goes quickly, we use a lot, and then it goes slower. But now we're not looking at the contents, we're looking at what is produced. So at the beginning, we had nothing that is produced, and it happened quite fast, and then it went slower. So we have quite fast at the beginning, and then slower. There where it goes slower, the reaction is completed, so that is 45 seconds. And the volume we've just calculated is 0.137.